Have any of you looked at your test results?
I checked and I didn't see them posted yet.
Okay, well, they're, I'm not sure I got to yours yet, Sally, because your name is towards the end.
Well, that would explain it.
Because I didn't finish them all. And the way you submitted it, it's fine. And you had mentioned you were going to get some help regarding the PDF version. So yeah, the only problem with the way you submitted it, I can grade it that way. It's just that it's a bunch of parts I have to put together. That's all. And you weren't the only one that did that either. There were about, I think, probably 5 or 6 you did the same thing. So anyway, before the next test where we're doing that, and for test 5, I'll just remind everyone to do a PDF. Okay. All right. So let's go ahead and continue on from Monday. So what we're going to do is, are there any questions from Monday? Did any of you try the 2 optional worksheets I included?
I started one of them. Oh, sorry if I cut someone off. I started one of them, but I haven't gotten to, I've mostly been answering the questions at the beginning. There were like 8 or 10 questions about physical and chemical changes and molecules and atoms. So I haven't gotten to, I think, this stuff yet too much, but.
Okay, well, that's fine. And there was one error that I corrected as well. So if you haven't downloaded them after that message I sent out, re-download it just to make sure you have the correction. Okay, so on Monday we talked about, one of the last things we talked about are things like a neutral atom and how many protons and neutrons, electrons, and a little bit of history. So I'm going to continue on from there. So what I'd like to do is review towards the end here, which is where the additional worksheets come in, and those I have under modules. Okay, so one of the big things that that this particular part didn't have is when you name the isotope, like this here. And I wanted to add that in early on rather than later, just so that it isn't an additional thing. So what I'm going to do is kind of go through, go through this again, just as a refresher, because this is going to get us into ions and isotopes. Okay, so right now we're dealing with a neutral atom. And what I mean by neutral is protons equals electrons. That means the net charge is going to be 0 because the pluses and minuses are 1-to-1 and they cancel each other out. Okay, now the situation you might ask yourself is, what if they're not equal? When protons and electrons are not equal, that means there's going to be a net charge, either negative or positive. And I'm going to talk about that in a minute or two. You guys better be quiet. All I have to say. Talking to my dogs, not you guys. All right, so let's look at this here. Okay, we've got a couple things here. Whenever we talk about an element, we always talk about its properties. And one of the properties are electrons and protons, neutrons in that element. And that's going to determine its chemistry, and it's going to determine its nuclear chemistry, and it's going to determine its physical characteristics, all those. The number of protons will determine what element we're talking about. And that's totally unique. It's a 1-to-1 correspondence. So when that number of protons change, so does the element. So if we go from 4 to 5 protons, the element is no longer the same element. If we change the number of neutrons and keep the protons the same, well, the element stays the same. It doesn't, its mass isn't the same though, because we have an extra proton or less protons, excuse me, extra neutrons or less neutrons. Because again, we cannot change the number of protons because that will change the element. Now, the code for this is Z is the number of protons or the atomic number, and that is referenced in the periodic table. Now, we haven't talked about periodic table yet, but all of you have seen probably a periodic table, which is going to look like this, okay? And there are two numbers in the periodic table. There's an integer, and that's going to be the Z number or the atomic number, and that's the number of protons. And there's going to be a decimal number most of the time. Okay, and that decimal number refers to the average number of isotopes. I'm going to talk about that later today. But there are always two numbers associated with each element. One is the number of protons or the atomic number Z, and then there's the average isotopes naturally occurring. Okay, so we're going to talk about each one of these in detail again. Okay, so let's go ahead and do this chart again like we did last time, just as a review, because it'll get us back into when we start talking about the ions. Now, okay, so this aluminum is aluminum 27. That's the particular isotope. And remember, the isotope is how many neutrons there are plus number of protons. So 13 plus 14 is 27. The subscript here is the number of protons. That then automatically goes to the element name. And that'll go, when you look at a periodic table, we're going to have an element name and an associated number of protons or an associated atomic number. Now, there are no exceptions to that. When that number of protons change, the element changes, period. Now, in nuclear chemistry, that happens all the time. You're always getting protons converted to neutrons and neutrons converted to protons, all that stuff. And when that happens, the element changes. Just like the alchemists talked about transmutation of elements. That's what happens in nuclear chemistry all the time. In non-nuclear chemistry, it doesn't happen. Okay. All right, so let's go on to the next one here. This is oxygen. What isotope is it? It's oxygen 16. Okay, oxygen has 8 protons. And we're talking about neutral elements here. So that means 0 charge. That means electrons and protons are equal. And we have 8 neutrons because we need to have a total of protons and neutrons equal to be 16. So if we have 8 protons, that means we have to have 8 neutrons so that we end up with 16. Now the worksheets, I think there are like, I don't know, 40 examples for ions, 40 examples for neutral. It really does a lot of these for you, lots and lots of practice. Okay, what carbon is this? Well, there's no way to tell other than we have 6 protons for sure, 6 electrons for sure, because we have a neutral carbon. We don't know what isotope we have for that. So let's choose carbon 14. That means we're going to have 8 neutrons. Same with sodium. It doesn't specify what isotope. So let's choose one here. And if we look at the periodic table here really quickly. Oh, let's choose sodium 23. Okay, and how many protons does sodium have? Again, from the periodic table. I should have a periodic table closer by. Let me get you C-stick here. Okay, notice it's going to be, for sodium, it's going to be 11. Yes, is that a question? Okay. All right, so how many protons? We have 11 protons, 11 electrons, because it's neutral. And then we have 11 plus what is 23, 12. So we have 12 neutrons. Now, is this starting to flow? I know we went over this on Monday, late in the day. The last thing we covered was this. So we're going to re-enter this again, because this is going to get us into ions in a minute here. All right, so what has 10 protons? Well, if we look on the periodic, I need to move a periodic table. Let me just move one up here. This one up here. Let's just move it. Should have had this more convenient for you. I'm sorry about that. Okay, so sorry about that. Okay, so what has 10 protons? Well, we're looking at neon. Okay, and what isomer is that? Well, if we add the protons and neutrons together, that's 20. So that's neon 20. Okay, what has 78 protons? Well, looking over here, it looks like we have platinum right here. And what isotope is that? Well, 117 and 78 is what? Well, let's see, that's 95. And lastly, we have what is 12 protons? That's going to be magnesium. And the isotope is 24. We have 12 protons, 12 neutrons. Okay, so that's kind of filling everything in for atomic mass. One of the things that this didn't talk about there's another number that my worksheets will talk about, and that's atomic mass. Now, the atomic mass is this number here, superscript. So for example, on the bottom one here, for magnesium, the atomic mass for magnesium is 24. That's P plus M. And that's the isotope, magnesium 24. Magnesium 25 is going to have a different atomic mass. So the atomic mass is not a decimal number. when I'm talking about a specific isotope. The decimal number on the periodic table is an average of all the isotopes in nature. We'll talk about that a little more in a little while here. Okay, all right, so let's now talk about, there are three kinds of situations when we're talking about atoms. Okay, we have a neutral charge. That means that the number of protons equals the number of electrons. We have something called an ion if the number of protons does not equal the number of electrons, in which case we're going to have a net charge, either positive or negative. And then we also have a situation where we have two elements where the protons are equal, but the neutrons are not. That's called an isotope. Okay, so let's delve now into this whole ion thing here. When an atom gains or loses an electron, or two or three, it will take on a charge because then the electrons don't equal protons. That means there's no net canceling of charge. So there's going to be a surplus of one or the other. If we have more if there are more protons than electrons, that means we have more positives than negatives. We're going to have a net positive charge. And there's a fancy name for that. In science, we always have names for everything in the world. That fancy name for that is called a cation. That's derived from electrochemistry. It's an ion that's attracted to the cathode. And that's where the cat part comes in. Now, it's easy to remember this as positive if you think of that T there as looking like that. The T looks like a positive charge. Okay, so more protons, that means there are more positives than negatives. Net positive charge. The name of the thing is called a cation. Conversely, when there are more electrons than there are protons, then it's a net negative charge, and it's called an anion. Think of the N as negative. So we have three situations. We have P's equal to E's. That's neutral. Net zero charge. P's are greater than E's. We have a positive charge forming a cation. P's less than E's. We have a negative charge forming an anion. Okay, so three situations. And we're looking at protons, electrons, and neutrons. We have to consider whether this is an ion or a neutral atom. Now, again, as I said on Monday, I need to tell you if it's an ion. I need to tell you if it's neutral. If I don't tell you it's neutral, I want you to assume it's neutral. But I'm always going to try to tell you it's neutral. But sometimes, for whatever reason, I forget. Okay? All right. Now, ions are charged. So we have to reflect that charge in the symbol over here. Okay. All right, so that charge is going to be reflected on how many protons or electrons are left over after they neutralize one another. So if we have 10 protons, 9 electrons, that means we have one left over or one positive charge. So looking down here, looking at magnesium, magnesium has got a Z of 12, or an atomic number of 12. We have 12 neutrons. That means we have 24 total for the atomic mass of that isotope. And because we have no charge, that means electrons and protons are equal. If we have an imbalance between protons and electrons, like here, we have one extra proton or one extra positive charge. Hence, it's going to be like that. Now, you will see, depending on what you're reading, it could be like this, like that, or like that. Those are all equivalent. And again, this is probably the more official way to do it, but you will see it the other two ways as well. Okay. In this third case here, we've got two extra protons over electrons. That means the charge is going to be positive 2. And because we have a positive charge, we have cations. Okay, so let's look at some ions now. And let's look at protons, neutrons, electrons for these guys. Okay, and the first one here, okay, this is it's a calcium-40 isotope. It's got no charge. That means protons and electrons are equal. And the second one here, we also have a calcium-40 isotope because we have 20 and 20 neutrons and protons adding to 40. But we have, when you look at electrons, we have one extra proton over electrons. That puts that charge at +1. And notice here, it's written as just a plus, indicating a +1, because the 1 is dropped. In the second one here with calcium +2, we've got 2 extra protons. That means a charge of +2. Looking at carbon 12 here, the electrons and protons are equal, so that means that is a neutral carbon. In this one here, we have carbon 14, and we have a -1 anion. Okay, so let's put the symbol there. Carbon 14 means we have 14 up here, 6 protons, and we have 8 neutrons, because 6 and 8 is 14. And because we have a -1 anion, that means we have to have 1 extra electron. That makes that 7 electrons. We have 6 protons, 8 neutrons, 7 electrons. Okay.
Can I
6
say
protons.
something, please?
Yes.
Somebody needs to unmute their mic because we have a really hard time hearing you.
Yes. Who's got their mic on? I think I fixed it.
Yes, that's much better. Thank you so much.
Thanks for telling me. All right. Okay. Okay, let's go to the next one here. Okay, we've got 6 protons. That's carbon again. And it's got 8 electrons versus 6 protons. That means it's got a charge of -2, and it's an anion. Six and 7 is 13, not 14. Okay, so let's go on here to oxygen. It's got a charge of -2, so it's an anion. And it's oxygen 16. -2 anion. 8 protons. 8 neutrons, because it's 16. We need 2 extra electrons because it's a charge of -2. That means it's got 10 electrons. 2 more than 8.
For carbon, wouldn't that be 12 since 6 protons and 6 neutrons would be 12?
Yes, you are absolutely right. You mean like that? Yes.
Yeah, that's what I was talking about.
And this would be. Okay, and then lastly, 7 protons. 7 protons is going to be. Let's see here. Let me grab the periodic table again here. That's up above. Okay, so what has 7 protons? Well, that's going to be 1 over from carbon. That's going to be nitrogen right here. Now, the good news on this worksheet, I want you to go back and forth between these symbols and the periodic table. Symbols, periodic table, back and forth, back and forth. So you get used to what those numbers mean on the periodic table. Okay, so that's nitrogen. And it is, what, 14 and 7 is 21. And it has 3 extra electrons, so that means it's a -3 anion. Okay, do those make sense? Do those fall into place? If you haven't done the worksheet yet, you can always come back to this video at this place. It'll show you how to do it. Okay, so let's talk in more detail about isotopes now. Are there any questions about these relationships with ions and neutral elements? Okay, in reiterating an isotope has the same number of protons, but different number of neutrons. Okay, and that's reflected in the number up here. Notice the number of protons is the same. That means they're both carbons because it's 6 protons. But this is the big deal with neutrons. Now, the chemistry of elements is not determined by the number of neutrons. It's determined by electrons. Electrons around the nucleus, and specifically the outermost electrons. I'm going to call those valence electrons in a little while. Okay, so electrons determine chemistry, neutrons do not. So the chemistry of carbon-12 and carbon-13 is extremely similar, if indistinguishable. Now, that has an advantage in nuclear, and should be in medical terms, because we can tag molecules. We can tag biochemical or organic molecules with an isotope that's different than the rest of the molecule. That's different from either extraneous or natural element molecules. And we can tag it and we can track it that way. You can also tag molecules with radioactive isotopes and go after, for example, cancer cells. So there's a lot of advantages by the fact that the chemistry is the same. What's different is the number of neutrons. Okay, so that's a big deal. Okay, so now we have, again, we have these three situations. We have a neutral atom, we have a positively charged atom, negatively charged atom or ions. And then we also have isotopes where the number of protons are the same, but the number of neutrons are not the same. Now, some isotopes are more stable than others. If they're more stable, that means we'll find more of them in the atmosphere. For example, if you can look down here at some of these. There's not a lot of hydrogen running around with one neutron in it. Now, these are percentages. These are percentages. Look at helium, different kinds of helium again. Some of these are in horrendous abundance, and others are a tiny, tiny bit. We talked about carbon-13. Notice it's only at a little over 1% versus 99% of carbon-12. Nitrogen-14 versus nitrogen-15. I mean, there's just certain ones that are much more abundant, and other ones are very scarce. Yes, there was a question? Okay. So these ratios is what gives rise to the gives rise to these decimal numbers in the periodic table. If we go over to hydrogen, notice hydrogen is 1.01. And if you remember from our table a few seconds ago, that hydrogen with no neutrons is like 99% abundant. And the one with one neutron is very scarce. So the number, the decimal number then is closest to the most abundant one in the atmosphere. Since it's closest to one, that means hydrogen 1 isotope is the most abundant. Beryllium 9. Sodium 23. Lithium 7. Potassium 39. Calcium 40. So those are the most abundant of the isotopes. But there are others. That's why it's a decimal, because it's an average. And when you average things, you always end up with decimals. Okay, so we've talked about labeling these, excuse me, already. So this is the element, and this is a particular isotope version of the element. Because they have the same name, that means the number of protons are equal. Because the isotope is different, that means they differ in the number of neutrons. So the difference between carbon 12 and 13 is only that. And reiterating again, the chemistry is going to be extremely similar. Using 100% because we have physical characteristics that are going to be different. And that can be, there's a lot of instrument techniques and stuff that will look for those differences. But basically, as far as 99% of the time, the chemistry is the same. You can't distinguish between when you're working with carbon 12 versus carbon 13. Nitrogen 14, nitrogen 15. Okay, nitrogen has 7 protons, 7 electrons. If it's neutral, nitrogen 14 and 7 neutrons. The 7 plus 7 is 14. In this case, we have 8 neutrons because 8 and 7 is 15. Oxygen is the next one over from nitrogen. That means it has 8 protons, 8 electrons, 8 neutrons because 8 plus 8 is 16. Oxygen 17 would have electrons and protons are going to be the same. So we're going to have 1 extra neutron. Okay, so atomic mass. We have the atomic mass of the isotope, and we have atomic mass average of all the isotopes. Okay, so I want to distinguish that because we have atomic mass for an isotope is going to be an integer. The atomic mass average is going to be the all naturally occurring isotopes in nature. Hence, decimal. Unless there's just one isotope, like with synthetically made elements, there's only one isotope, so that means it's not a decimal. Okay, all right. So to calculate all of this, we need to know the mass of each isotope. That can be found for example, here we have gallium, and that's the mass in atomic mass units, AMUs or U's. And later we're going to find out in unit 5, it's also going to be in grams. So AMUs, U's, and grams for atomic mass, okay? But don't worry about grams now. We'll get to that in extreme detail in unit 5. Okay, so this particular isotope of gallium has a mass of 68,925,6 U's or AMUs. And it's 60%, 60.11%. Gallium 71, it's got that mass with a percent of that. And these are natural occurring isotopes of gallium. So we need to find the average, and we average all that stuff together, okay? So we're taking, this is the percent converted to a decimal, percent converted to a decimal, that's the mass. So we multiply the percent times the mass plus the percent times the mass, add those together, we'll get our average mass, or AMUs. Let's look at this problem here. It says carbon has two naturally occurring isotopes, mass of 12.00000 and 13.00033, blah, 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 AMUs, okay? And we have 98% of this one and a little over 1% of this one. So we're going to convert the 98.93% to a decimal. Times the AMUs of carbon 12. Doing the same thing over here, converting the 1.07% to a decimal, times the mass of the carbon 13, adding those together, we'll get 12 point blah, 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 blah. Now, if you look on the periodic table, they round it to 12.01. But again, since it's close to 12, then we know that it has more 12s than anything else. And because it's greater than 12, then most of the isotopes are greater than 12. If it was like 11.95, then most of the other isotopes are going to be less than 12. So if you look at our periodic table, this one, for example, you can see it is 12.1 here. Okay. All right, so that's isotopes, and there are abundance of them around. There's always one that is horrendously more stable than others. Sometimes it's hugely more stable. Sometimes it's just more stable. Like with gallium, it was 60-40 basically. But with carbon, it was 99 basically versus 1. So some are, it depends on the element. And there's in Chem 400, you'll talk about why one is more stable than another. Okay. All right, so I'm going to talk now about the periodic table. Are there any questions about isotopes, ions, number of protons, electrons, neutrons that we've gone through?
I have a question about ions.
Yeah.
So these elements that exist, can they have any possible net charge out there, or is it that they can either be, like, for example, negative and neutral, or positive and neutral? Like, can carbon be negative, positive, and neutral?
Yeah, that's a really good question. We're going to talk extensively about that in this course. But for now, I'm going to answer yes. And of course, what drives the abundance of anything? What have I harped on this class?
Stability.
Exactly. So certain elements exist as an ion because why? They're more stable. Some exist neutral because why? They're more stable. Now, I'll mention that briefly here. We're going to talk about why that is as the semester progresses. And it has to do with the arrangement of the electrons around the nucleus. Some arrangements are more stable than others.
Okay, sounds good. Thank you.
You're welcome. So what the element wants to do is, if it isn't stable, it'll either gain or lose electrons to become more stable. And in that case, that's when the ions form. But that was a really good question. So here we have, and we go all the way out to here. These are all filled in now, all the way out to here. So we have 118 elements running around. A number of them are artificially made. Everything past here, from 93 on, is artificially made. So the last naturally occurring element is uranium. It's also very, very large. And the larger these elements become, they become very cumbersome because they have a whole bunch of neutrons and protons running around. I mean, look at this uranium here. You have 238 protons and neutrons around that nucleus, or inside the nucleus, and an associated number of electrons buzzing around it as well to equal it. So they're very cumbersome. And when we start making them bigger, they become even more cumbersome. Hence, the stability goes down. Now, some of the man-made elements like plutonium, unfortunately, are pretty stable and also very, very, very deadly. Some of the other ones aren't as bad, but plutonium is bad. Okay. All right. So this is your typical periodic table. And again, I want to remind you that these are all filled in here. Now, these are filled in the last like 5 years. So this is pretty current stuff, but it does go all the way out to 118. Okay. In every box, each box is represented by an element. And the element, and again, it depends on the periodic table. Some periodic tables have a name and some don't. Some periodic tables have decimal places that go way out, like 7 and 8 decimal places. And other ones are averaged to 2 decimal places, like this particular one. So it varies. The other thing is you're going to see is a difference right here. And it depends on where these 2 elements are. Either they're there or they're down here. So you'll see 2 variations of the periodic table based on that. Now what I want to do is I'm going to bring down this guy. Okay, notice see the difference between the 2? In this case, the lanthanide and actinide are up here, and down here, they're down here. In 1947, this caused a huge controversy in the American Chemical Society. In that meeting, half the chemists walked out because there was a proposal that they move these guys down here rather than keeping them up here. Half the people walked out, hence 2 periodic tables. And they're subtly different, but We're going to talk about the differences between these two later on, but you will see there is a slight difference between the two periodic tables fluctuating. Also, the number of decimal places on the average atomic mass that will fluctuate as well. Either it'll be rounded off to 2 decimal places, or it'll be some huge amount of decimal places either way. But this is a interesting difference. And that American Chemical Society International meeting, literally half the people walked out because they didn't agree with the decision to move it down there. It's a big deal. Okay. We're going to be using this periodic table a lot in this course, a lot. So for right now, I want to get on some basics here. The way it's a 2-dimensional table. The reason it's 2-dimensional is way back when it the way this all started was before about 1850-ish. There were a lot of elements around, and they didn't have any real organization. So what a geologist and a physicist started to do was they started to organize the elements by their chemical characteristics. And they just start putting them in like this, all the elements available at the time, by increasing mass. So this would be mass. And what they noticed was every now and then, the chemical nature of the elements started to be similar. For example, as they're going along, they noticed that lithium and hydrogen had similar chemical chemistry, its chemical nature, the ions it formed were similar, almost the same. And they noticed that about a number of elements. So instead of being one-dimensional like this, they decided to go 2-dimensional. And when they went 2-dimensional, they started splitting up all the chemistry that's the same. And they put that under one another. So the lithium, they broke it here and moved this over here underneath hydrogen. That's why lithium now is under hydrogen. Then they noticed that neon has the same chemical characteristics as helium. Argon, krypton, xenon, etc. These all have similar chemistry. So they took the one-dimensional model and broke it up by chemical nature or chemical characteristics. That's why we have a 2-dimensional periodic table instead of a one-dimensional one. So that says a lot about the periodic table. It's very handy. So I want to talk about how this thing is organized. First of all, we've got this black squiggly line here. So there are three basic parts of the periodic table. Metals, non-metals. So if it's not a metal, it's a non-metal. And then something called metalloids, which have the characteristic both of metals and non-metals, depending upon how you treat them. And usually they're treated with something like a voltage. In other words, if you apply a positive voltage or a negative voltage, they change their characteristics. Notice that most of the elements are metals. Then comes non-metals, and lastly, metalloids. So a lot of you would be able to describe metals. You know, they're shiny, they can conduct electricity. That's why they make wires out of metal. You can bend them, you can stretch them. They're shiny, a whole bunch of characteristics that you could probably pretty much come up with on your own. Possibly the conductivity and stretching and malleability may not, but basically you're comfortable with something that's a metal. Non-metals are kind of the opposite of metals. So if a metal is shiny, a non-metal is dull. If a metal can easily bend and stretch, non-metals shatter. If metals conduct electricity, non-metals won't. And then metalloids can be changed from acting like a metal or acting like a non-metal. That's where our whole digital world is based upon our metalloids. In fact, I have a student that created a hat for me that said metalloids are cool. That's, because our whole digital evolution is based upon 1947 Bell Labs invented the transistor. Before that, they used vacuum tubes. Vacuum tubes are very cumbersome. They're horrendously energy wasteful. They get very hot and they're big. Transistors were pretty good size in 1947, but over the years, over the decades, they've shrunk down to horrendously small. And that's why you can have a whole bunch of stuff in your phone, because transistors are so incredibly tiny now. In 1947, Bell Labs is the early AT&T, and up in Chicago areas where they invented them. So the United States invented the transistor, and obviously it spread all over the world. Now, as far as our class is concerned, I want you to know some things about the periodic table. One, how it's organized. Now remember, the next test is not going to be take home. It's going to be a multiple choice or fill in. Okay, so you need to know how it's organized. Number one, metals, non-metals, metalloids. Number two, I want you to know 4 groups. Now, groups are vertical columns. And there's a whole bunch of them. Now, a group, because of the way the periodic table was invented, that's where the one-dimensional was broken where the characteristics, chemical characteristics are the same. So everything in the group is going to have same chemical nature, same characteristics, the same reactions. So alkali metals, that's one group you have to know. Alkali earth metals, either alkaline earth metals or alkali earth metals is another group. And these groups are very common. Very common. You'll see them throughout your study of chemistry. You'll see them in biology, particularly molecular biology. You'll see them in certain physics curriculum. You'll see them in geology. They're very common, these four. Now, every group has a name, and they're very strange, some of these names, and they aren't used very often. These four I'm going to have you know are used often. Okay? Halogens and noble gases. Those four groups I want you to know. Going back to, I forgot who asked the question about whether the elements are ions or neutral compounds, and I talked about stability. Group 1, or the alkali metals, aren't particularly stable. So what happens is they like to form a +1 cation, and they're much more stable. So if you were going to look for sodium in our world, you'll find it as this +1 ion, not as sodium element. Sodium element is very unstable, and you won't find it. You'll find it, horrendous amount of it, as the +1 cation. The alkali earth metals, +2. +3 for the boron group. Starting with the halogens. Halogens form anions, -1. The next one over, -2, -3. Now notice we kind of come together with a -3, a +3, -3. What do you think is in the middle here? Right here.
0.
Yes, very intuitive. Because, following the logic, it's either going to be +4 or -4, right? So what happens is it does neither, and it's 0. You're right, absolutely right. Very good. So in other words, the group carbon is in is usually found in nature the way it is. So it doesn't form ions easily. Now, I didn't mention any of these transition metals here. They do form cations, though, but they're not one particular cation. And we're going to talk a lot about this later on. Basically, all the metals form cations. The non-metals form anions. Now, the noble gases, they are found a lot in nature as is. So that tells you they're really stable the way they are. Now, the reason why they're called noble gases, it's really an old term. It has to do with going back to the royalty of Western Europe at the time. And the royalty did not socialize at all with the plebes, the plebeians, the common folk. They were strictly by themselves. So the noble gases tend to be by themselves. They don't interact with anything else. So they're very stable. I'm going to talk about why they're stable as well. So going back up here, it's also going to be 0. Now the problem with carbon, carbon doesn't form ions, but it's not particularly stable either. So it's everything that carbon does has to form with something else because by itself it's not stable. Okay. Now there are some trends. I want to talk about. Okay, and I can't really read that. Okay, element 87, francium, and element 9, fluorine, are the two kind of mileposts in this trend. Let's see, I'm going to pull this guy. Okay, so this is going to be our trends. And okay, trend number 1. Okay. As we go from top right to bottom left, things get bigger. So the smallest element is fluorine. The largest one is francium. Now, there's a couple reasons for that. Mainly, if you think about it, francium has 87 protons and a total of protons and neutrons of 223. So think about a bag of marbles. Fluorine has got 19 protons and neutrons. Francium has 223. Which bag of marbles is bigger?
Francium.
Yeah, because it's got more stuff in it. Yeah, that's the easiest way to remember this. Now, as you go across the periodic table here, things get smaller as well. That's why on the left side they're bigger, on the right side they're smaller. But the major trend is top right to bottom left using fluorine and francium. Something called electronegativity. In fact, let's do that. Okay, that's the tendency for an atom to attract It's a tendency for an atom to attract an adjacent atom's electrons. Kind of power hungry. They want to suck those electrons in. And why do you think that's so? What rules the roost in the universe?
It has a positive charge.
It has a negative or positive charge depending on which electronegativity is stronger. All the atoms, I'm going to show you Monday, an electronegativity chart on the periodic table. All the elements have a value of electronegativity. The higher the electronegativity, the higher the tendency to pull or attract the atom's electrons next to it. And it's for, again, stability reasons. Okay, and that trend is the opposite. I'm going to abbreviate this as EN. Okay, so that goes from francium up to fluorine. So fluorine has the most electronegativity of anything in the periodic table. Francium has the least. Those are the two major trends for right now. We're going to talk about some more later, but these are the two main ones I want you to know. Electronegativity, which is the tendency for one atom to attract the adjacent atom's electrons, or electron cloud, we'll see later, and then size. And we haven't talked about valence electrons at all yet. There are two kinds of electrons, valence and core. I'm going to talk about those I believe on Monday. Okay, so I'm very specific on these trends, two trends right now. Okay, electronegativity, and that plays a major role in forming these ions. Because notice, the top right is where all the electronegativity is. Notice the top right is where all the anions form. That's where those elements want electrons for stability reasons. Down here, they're getting rid of electrons for stability reasons. So they have a very low electronegativity. So the higher the electronegativity, the more they want to form anions. The lower the electronegativity, the more they want to form cations. And we're going to talk about this again and again and again. It's again for stability reasons. Okay, so we are finished with chapter 4. And what we do is we have a summary here. Now, what I'd like to do is go over these on Monday to bring this chapter together because it'll introduce chapter 9. That's our third chapter for unit 2. So we have ions, we have isotopes, we have neutral ions, we have what is charge, how the periodic table organized, excuse me, some groups within the periodic table, how the model, how the atom is set up, a little bit on some of the historical aspects of the development of the atomic model. That's what are covered in chapter 4. Okay.
So the next test is going to be on chapter 4 and 9.
3, 4, and 9. Mostly on 4 and 9. So yes, 4 and 9. But it'll cover some parts of 3 as well. I'll give you a study guide for the test. Make sure you, I'll say it's going to cover this. Boom, 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 boom. So make sure when you're going over worksheets. And a lot of test questions come from worksheets that I modify. So keep that in mind as well. That's why it's important to do the worksheets, because if you don't do the worksheets, all the problems on the test are going to be totally new for you. It's not saying you won't do well on the test, but they will be new for you, and the chances are lower that you'll do well if you've never seen the questions, similar questions before. Also, we're going to be getting into labs very shortly as well, and I'll talk in detail about that. That's going to be videos as well. Okay. Go ahead and check over your tests. You should be able to see a corrected copy of your test. If you're missing something, I'll have annotated it, and I haven't finished them all. I will finish them though by this evening.
Thank you so much. Have a great night.